I'd like to introduce some tools provided by Intel, which can help the design of multi-threaded programs. In particular, we're going to discuss Intel's compiler and VTune performance analyzer tool. Two of the tools that Intel provides make multi-threading easier and more comprehensive. One is the compiler. Intel's compiler has a lot of new features that will accelerate application performance, and it will optimize your application towards multi-core design. On the other hand, Intel's VTune performance analyzer tool can identify your program sections where you can make it multi-threaded. VTune tool can also be used to monitor performance of the applications and provide hints to the designers where they can optimize the design. Intel's compilers supports a lot of features, 32-bit, also 64-bit architecture, and it supports Intel's Titanium architecture as well. It can be used with Microsoft Visual Plus C++, GNU C++, or other programming languages. It offers several advanced optimization techniques, and it provides support to multi-threaded programs. It is compatible with industry standards, and it can compile applications for both 32-bit and 64-bit environment. Not different from other compilers, Intel's compilers utilize different switches to enable or disable certain optimization features. For example, this -0, this is the switch that you can use to disable optimization. This is helpful when you debug your program. As you do source code level debugging, if you turn on optimization, the breakpoint that the debugger stops at may not reflect your exact source code lines. So in the development phase, you may need to disable optimization. For -G is to create symbols and also symbol information to assist in the debugging process. And the other options, for example, O1 and O2, are different levels of optimization that you can use in your final binary. And some features or switches specific to Intel's processors. This one is -AXP, that's specific to Intel's SIMD, or single instruction multiple data instructions. The other ones, for example, O3, can be used for optimized data cache for floating point code. A new concept here, maybe a new one to some of you, profile guided optimization. Profile is a way to, or profiling is a way to understand the runtime characteristic of an application. And this profile guided optimization, or PGO, is used for analyzing application code at runtime. Now, when you design a C code, you can provide some information in the source code the compiler can utilize to do the optimization. For example, if you have loops, you can allow the compiler to do some loop unrolling. But some of the things the compiler does not know until the program is actually executed at least once on the target processor. And this is what we call profiling. So profiling is a technique that you can use to run the binary code on a processor once. And during this run, you will collect a lot of information. For example, the memory footprint size, how this application utilizes the caches. So this information can be used by the compiler again when the compiler is chosen to do this profile guided optimization. PGO will detect and provide opportunities to optimize the performance of the application. It can reorder functions, reorganize the code layout for improved instruction cache memory utilization. This figure illustrates the process. PGO is a three-stage process. In the first step, you have the source code, and you compile with one switch turned on, or prof gen. So the compiler will generate a code that embedded with instrumentation coding. With this code, you will run it on the target processor. So this code is different from the code you generate without this prof gen switch on. This code has smaller pieces of add-ons so that when you execute this binary on your processor, it will not only finish the program. Okay, if it is doing matrix multiplication, it will certainly perform that. But in addition, it will generate a lot of information we call dynamic runtime information. This additional information can later be used in the third step. As you can see here, this information is coupled together with the source code. So compiler now has more knowledge of your code because it is executed once. So with these two pieces of information, the runtime information and the source code, if we turn on this profile use switch in a compiling process, we will be able to generate a final binary code which is more efficient than the first code you generated. The PGO performs the following optimizations. For example, basic block ordering. It can provide better register allocation. You may use more or less registers depending on the runtime information. Other benefits could be switch statement optimization. For example, if you have a switch statement in your C code, let's say you have 20 cases in your C code, and it turns out that the very last, the 20th case is the most frequently used case. So when the compiler generates binary code, this first case will be actually put in the first condition checking in the binary. So that will help the performance. As we just saw, this PGO process will use the prof gen switch for optimization. It enables use of two Intel tools, code coverage and test pre-authorization. Inter-Procedural Optimization is another possible optimization by Intel's compilers. It can perform a static analysis of the application link time with details of the variables and functions seen during a link setup. Compiler-based vectorization. This is particular to Intel's single instruction multiple data extensions, or SIMD extensions. Intel calls this as SSE. They have different generations, generation 1, 2, now they have generation 4. These instructions essentially work on vectors. So it works on an array of data, either bytes or words or double words. So instead of doing addition on one byte to another, it's doing addition on 16 bytes on another 16 bytes with one instruction. So that's the benefit of doing this SIMD. As you can imagine, this type of instructions are very useful in multimedia and DSP applications where you are recently dealing with a lot of data, but the operations on these data are the same. There's an example in the Prescott new instruction. This is the SSE instructions. This is the third iteration of the SSE instruction set for the IE36 architecture. As you can see that the very first generation of SIMD in Intel's processors, they can do operations on 16 bytes at a time, or 8 words at a time, or 4 double words at a time, or 2 quad words at a time. For the first generation, third generation, these instructions are expanded to other data units. For example, in the SSE 2 and 3, the Intel processor can do 2 double floating point numbers operation. You can turn on or off these compiler-based optimization when using the compiler. Different switches can be used here. I will skip this detail. Now to the VTune Performance Analyzer. So this is the second part of the lecture. In the earlier slides, we talked about the compilers. Now this VTune Performance Analyzer is actually a tool that is available on Windows or Linux. And this tool is supported by Intel. It's a tool that you can use to analyze your executable file. So if you create an application, you have an executable, you can run it on your target platform, either Windows or Linux. And while you are running your program, you can use this VTune tool to gather information of your program. It can collect, analyze, and display performance data for a variety of applications. Specifically, this tool, VTune tool, collects performance data from the system, from either Windows or Linux system. It will organize and display the data in a variety of interactive views. The goal is to help you identify potential performance issues and provide some suggestions. There are 2 ways you can run it. One is called native data collection, and the other one is called remote data collection. These 2 differ in that where you run this VTune tool. Let's say your target application, the software you design, is running on this processor A or this computer A. You can run VTune tool on the same machine. This is what we call the native data collection. So the VTune tool will be able to directly extract the performance data from the same computer. In contrast, you can run VTune tool on the remote machine. Of course, you need to have some helper threads that running on the host machine, and this helper thread will be able to collect the data and send the data over the network to the remote machine you are running VTune tool. So this is what we call remote data collection. You can do this native performance analysis using this native data collection for any of these following processor families: IE32 processors or INT family processors. You can also, like we're shown here, collect the performance data remotely. So you have a host system and a target system. And this is the system you want to monitor the performance. And you can run a VTune tool here and control the target. Now, what does the VTune do exactly? It's going to do these several things. It's going to sampling, which is to calculate the performance of application over a period of time for various processor events. So it will know how many times your application accesses, say, layer 2 cache memory. Also, it will use the trace of your binary execution. It will build a call graph. So what is a call graph? If you write a C code, you start with the main program or main function. In your main function, you call other functions you design. And your other function may call a third party's library. So you have this call sequence or a chain. And eventually your program finishes. That's after you finish all the function calls. So this call graph will build a graph that shows the call relationships among all these functions involved in the execution. So if function A calls function B, so that will be a pointer from A to B. And if your function B calls library C, there will be a pointer from B to C. So the VTune tool will provide a graphic view of the flow of the function calls. It will provide also a counter monitor, so it will show the resource utilization. And one interesting feature or capability is the Hotspot view. This essentially is going to guide you to optimize your code, because Hotspot view tells you in your program, out of your 10 millions of instructions, what segment of a code at hotspot are executed, say, 10,000 times, whereas compared to 99% of your code might only be executed once. So this hotspot view will provide you a very useful information on how to optimize your code. And also it has the tuning assistant to give you advice on analyzing the performance data. Sampling is the process of collecting performance data. It will be able to identify hotspots. For example, there might be a section of the code that is executed millions of times or consumes a lot of CPU cycles or generate many cache misses. Sampling can also identify bottlenecks. It will show areas that can slow down the overall execution of your program. Due to the time limit, I will not do the demo, but I will show you some string captures. Let's see, it's not very clear here. Let me move on to a different one. Okay, so this is what you would see when you start this VTune tool. So it's essentially a Windows application. And in this application, you will be able to select the other application that you want to monitor. So you will see the processes that's currently running on your system, or you can select the executable you want to start. Once you start the application or the process, this VTune will be able to have an entry in this view here, so you can click that process and you can do start sampling. So after, say, 10 seconds or after your program finishes, it will produce data about how many processor cycles are consumed by the application, and the call graphs, and also some other resource utilization of your application. Yep. So for Intel processors, you can essentially do it on all the modern processors. And it has Windows version and Linux version of this tool. You can get a 30-day free trial of this tool from Intel's website. You can use it to try it out. And I think I should be able to get some academic license so that we can use it permanently. Let's see. You can do time-based sampling, which will help you understand where the application spends most of the time. You can also do event-based sampling, so you can, let's say, you can try to pin into processor events. For example, L2 cache misses, branch mispredictions, and also how many instructions committed overall for floating point operations. And this is a figure that shows sampling over time, and it will show how often these functions are called. For call graph, I don't have a picture here. Essentially, call graph profiling will be able to generate finally a big graph that shows you the what is the caller, what is the callee among these functions out of the whole execution phase. Okay, I have a call graph view here. So you're going to see something like this. This is from the main program. It calls functions, and function calls sub-functions. It may call the function multiple times. It will show that how many times it's called, and so on. So you can have a global view of the binary code. And some of the code, for example here, the bright orange code indicates functions with the highest self-time. So that's where most of your CPU cycles are spent. So that's the function you want to look into to see if you can further optimize the design or even make it parallelized in executed by multiple threads. Okay, so there are a lot of features from this VTune tool, and I encourage you to try to download a copy of it, try to run it on your machine to test out these features, at least to get yourself a quick introduction of these tools that you might need in your future project to optimize the performance of the applications.